Okay, so for today, we are looking at another ultrasound question. Let's read it out. So, in an experiment, a beam of ultrasound is directed at the boundary between two materials A and B. Figure 24.1 shows the beam incident at right angles to the boundary between these two materials. The material A is unchanged. The acoustic impedance of material A is 2.5 times 10 to the power of 6 kilograms per meter squared per second. The material B is varied. The acoustic impedance of B is Z. Figure 24.2 shows the variation with Z of the percentage of reflected intensity of the ultrasound at the boundary. Right, so figure 24.1 has ultrasound going, the ultrasound is going into the material B, so it's going from the left to the right. And figure 24.2, you've got on the y-axis, you've got percentage, reflected intensity as a percentage, and on the x-axis, you've got Z measured in 10 to the power of 6 kilograms per meter squared per second. So remember, in these questions, you've got to look at the axis, look at the axes. Explain why the curve shown in figure 24.2 has a dip. All right, just look at this question. It's got 3 marks. So if we were to describe the graph as Z increases from 1 to about 2.5 roughly, it's going down. So the reflected intensity has gone down from 1 to 2.5 roughly. And then from 2.5 onwards, the reflected intensity increases. So that's just describing. Now we got to explain, and that is 3 marks. All right, how do we do this question? Okay, so you're given that A on the left-hand side is 2.5 times 10 to the power 6. And on the right-hand side, you've got just Z. So here you have ultrasound coming from the left. Now, if Z, because you have two different materials, you will have some of the ultrasound being transmitted, some of it will be reflected. Now, I gave you the equation yesterday, and that was Z1 minus Z2 over Z1 plus Z2 all squared. Okay. However, mathematically, it doesn't matter if you swap them around, because as long as the bottom is plus and the top is negative and you're squaring it, the answer will be the same. So the correct formula, the one that you're given in the book, you have Z2 minus Z1, Z2 plus Z1. Now the reason why that's Z2 minus Z1 is because Z2 is the second material, and you're taking away from the second material to get the reflected intensity. However, mathematically, it doesn't matter, but this is the correct formula, and this is what you're given in the data booklet. Now, if Z2 is equal to Z1, that would mean that the top is equal to 0. And if that is equal to 0, because Z1 is equal to Z2, what does it mean? That means the reflected intensity is equal to 0. So if that and that is the same, you're taking away the same number, that is equal to 0, that is equal to 0. So if you have the same material, the ultrasound will just go straight through. If you have two different materials, because there's a boundary, then some of it will be transmitted, some of it will be reflected. All right, so let's just go back to that graph. I'm just doing it from memory. So the bottom here was Z, and here was the percentage intensity. Here was around 2.5, so something like this. So what happens at this point? So let's just put the numbers in first. You know that the second material is Z. So that is Z minus 2.5 times 10 to the power 6. and the bottom is Z plus 2.5 times 10 to the power 6, and that is all squared. Right, so this is what the graph actually looks like. So if I just write down IR over I naught equals this, okay? So because this is the percentage or the fraction that is being reflected, imagine that this is the y variable and the x variable is the x variable. Z is the x variable. So imagine that this is y and this is x. This is what the graph would look like. So if z was equal to 2.5 times 10 to the power 6, which is at this point, there is no reflection. That is because it's the same material. The ultrasound will just go straight through. There is no reflection. If z is different from 2.5 times 10 to the power 6, you will get some reflection. That's why you get these lines here. Okay, so how would you write this down then? So number one, you write down the equation. The equation is this. And then, of course, you can stop it in. So if you were to say that this was equal to 2.5 times 10 to the power 6, this was equal to z, that will give you the mark. 2. What happens when z2 is equal to 2.5 times 10 to the power 6? That is when these two are the same. When you take them away, you get 0, and therefore IR is equal to 0. Now, this can't be equal to 0. Well, I mean, because the whole thing is equal to 0, only the top is equal to 0. It wouldn't make sense if that was equal to 0 because you must have some original intensity going in. So when z is equal to 2.5 times 10 to the power 6, would you get no reflection because it has the same acoustic impedance, it is the same material. So you can say it's acoustic matching. And then for the third mark, what you've got to say is that what happens when z is not equal to that. So when z is not equal to that, that means you have different material and some of it will be transmitted, some of it will get reflected. So when z is not equal to 2.5 times 10 to the power 6, you have reflection. Let's have a look at this question. Here it says, describe and explain a method using ultrasound to determine the speed of blood in an artery in an arm. State one major advantage of this technique for the patient. Now, this is a 4-mark question. All right, so how do we do this question? Let's just draw the blood vessel. And the transducer is at an angle like so. It's emitting ultrasound. So this angle is here. You've got blood cells. Let's just assuming it's moving this way. So now the blood cells is moving away from the transducer. So the reflected wavelength will be longer. So it's due to the Doppler effect, because it's moving away. When the reflected ultrasound is received, the wavelength will be longer. If you think about it as redshift. Now you're given the equation in the data booklet. You're given the equation delta F divided by F is equal to 2V cos theta divided by C. F is the frequency of the original ultrasound wave. Delta F is the change in frequency. V is the speed of blood. Theta is the angle between the transducer and the blood vessel. And C is the speed of ultrasound. All right, so how do we do this question? Now, if the transducer was 90 degrees and the blood cells is moving like so, if it was 90 degrees, it's hard to detect the change in frequency because it's moving past that point. The ultrasound is going this way, but the blood cells are moving that way. So it's very difficult to measure the change in frequency. If it was at an angle, it is much easier. So that's the answer for the first mark. You write down, because it is at an angle, the moving blood cells will reflect the ultrasound. Okay, so that's the first mark. 2, there will be a change in frequency. So because it's, if the blood cells were moving away, the wavelength will get longer. And you know that if you use the equation V equals F lambda, also, because even if you, the change in frequency would mean a change in wavelength. So here, if you just remember that this, let's draw this here. So here, the frequency is higher, the frequency is lower, but the wavelength here is shorter and the wavelength here is longer. So because there's a change in frequency, that also results in the changing of the wavelength. So, you could say because there's a change in frequency, that would also imply there's a change in wavelength. Okay, so the third mark for saying, now you need to look at this equation here, because this is the changing frequency, and it is directly proportional to here. And what's V? V is the speed of blood. So the faster the speed of blood, the bigger the change. So faster the blood, the bigger the change. And then the fourth mark, why do we use ultrasound rather than X-rays? Because it is non-invasive. Invasive. And there's little to no risk of infection. Okay, so number 1, if it was 90 degrees, it's very hard to detect the changing wavelength. So it is at an angle, the moving blood cells will reflect the ultrasound. Number 2, there's a change in frequency. That's how we can detect the speed of blood. Also, the change in frequency would mean that the wavelength is also changing. The faster the blood, the bigger the change. And because we're using ultrasound, it is non-invasive, little or no risk of infection.